Good evening, everybody. So let us start our lecture today, and then today is October 5th, 2021. So there are a few announcements. First of all, then as you got your test 1 back, I will upload the test 1 grades. And if you have any question about your test 1 grade, please say me, okay, or email me. Okay, and then let me see. Quiz 3 is uploaded, and maybe assignment 3. Okay, so this will be due this weekend. Quiz 3 and assignment 3. Okay, please start it ahead of time. So the assignment especially start it ahead of time. You don't need to do one time on it. So you can do time to time and then try to understand. Okay, I will grade assignment 2 in coming week. I was busy in grading stuff. Okay, and then what else? Okay, another thing is that I uploaded red black tree PowerPoint slide. Just download it. Okay, so you get it and then click over here and download it. Okay, and sometimes I upload PowerPoint raw file so that if you find something else better or if you understand better, you edit it and add your own technique over here. Okay, and keep it. So in our last lecture we were discussing how to do insertion with an example, just with an illustration, to do an example with in a red black tree. Okay, I skipped the algorithm today, insertion algorithm last week. Today I will cover the insertion algorithm. So you see that I skipped some slides. I will cover those one. Okay, so in our last lecture, what did we? Let me recap it quickly. We got some data. Okay, and then we started. So let us recap quickly what are the properties of a red black tree. There are 5 properties, right? Number 1 is yes, all nodes are red or black. The number 2, yeah, root is always black, right? Okay, number 3, leaves are black. Okay, and number 4, if a node is red, then both children are black, but the opposite order is not a restriction, right? And then what is the last one? In all path, number of black nodes same, right? Okay. So we keeping those properties in mind, so we learn how to insert some nodes with data in a red black tree. So and additional rule was that initially, what is the insertion rule? That initially a newborn node is black, red, right? So here this one, whenever this is empty, then we started a newborn child and it's red color, and then we matched all of the properties. So in one of the properties we know that a root must be black, so we recolored it, right? And then it's okay. Although it has some leaf nodes, we skip the leaf nodes. We don't need leaf nodes, so originally all side leaf nodes are same, right? Okay. And then when we inserted 2 initially as a red, and then now we have 2 nodes, and then we checked whether all of the properties match. Okay, so its root, its father is black, so no problem, right? And then root is black, is okay, so then 2 is inserted, fine. Okay, so as we know that this is a red black tree is a BST, binary search tree, so 2 will go right side, 2 will be right side. Okay, it never can come left side of 1. Remember that, okay? It's a binary search tree. Okay, then when we insert 3, so we inserted 3 over here, then 2, then it violated some properties, right? Number 1 property is violated, that if a parent is red, then child must be black, right? Cannot be red. So whatever we did, we make it black. So in that case, it violates another property. What is the property it violates? Which property is violates? Last one, right? The number of black nodes. You can do this way. You can do either from here to this one or here to this one. Rotation. Okay. So here actually we don't need to rotation, and first of all we should take care of this one. So it violates the black number of black rows. So what do we need to do? We did another rotation, right? So right to right, then we did left rotation, then we got this way. So then still now it violates another property. What is that one? Root is not black, right? So we made the root black, and then now it is okay. So by looking this, then we see that in a red black tree, it is not required to have any red node, right? Here also all of the nodes are black, but still it is a red black tree. This one, the last one. Understand? Okay. So now when we insert 4, right? When we insert 4, so is it okay? So I don't see any issue. So on the right side, number of nodes is black node is 2, and this number of black node is 2, and then its parent is root is black, okay, and its parent is black, no problem, right? So 4 is added nicely, and then it will make an issue when you add 5, right? So when you add 5, then its root is red, its parent is red, so we need to change its color. If a child color does not match, do it immediately. But if it does not confirm, we will see the algorithm actually. It does not fix, then we need to change the parent color. First we need to change the child color itself. Okay, and do this way. So the next few slides are straightforward. So please download this and then go through each of these slides and then try to understand. Okay, so in your test, I will give you some example like this, and you have to write your red black tree, and unless you understand clearly here, you should not be able to study it during test time and then answer it. Okay, so the last one. So whenever we did this one, we got this one, right? Finally, so you see that although the data came as in ascending order, but the finally red black tree is not you see that not it look like that much balanced, but it is balanced. It's pretty balanced in terms of number of black trees. So now let us check whether it is a red black tree or not. So another condition is that root is black, is okay. So number of black in this side 1 2 3, this side 1 2 3, this route 1 2 3, this route 1 2 3, this route 1 2 3. So all properties match, and this is red, so all this black, and this is black, both red. It's not an issue. Now does anyone has any question about until this that we discussed in our last week? Yes.
I actually thought that like the maximum length could only differ by 1, like for each subtree, like to be balanced, because you have a depth of.
That is an AVL tree. That is the property of AVL tree.
So that doesn't apply here.
No, we are considering the only, so you can consider that black node over here. If you want to consider the number of nodes over here, the 5 properties we saw for, good question though, thank you. For a red black tree, there is no property that. Is there any property that says that number of difference of length should be maximum 1? It does not say that. Okay. Okay, but good question though. That is for AVL tree. That property is for. Okay, anyone has any other question? Okay, now I have a question. Now, in red black tree, in our last lecture we discussed rotation, right? Rotation, not regular rotation, that not the AVL tree rotation. Rotation with branch. Okay, like last lecture I discussed with example. Now let us do it. Everybody, please open your pencil and open your paper and pencil. Let us do an activity. For this tree, okay, we need to make a rotation. This is, for instance, this is x, 6 is x, okay, and 8 is y. So we need to rotate it. Oh no, not y is 6 and then x is 4. Okay, so we need to rotate it on 6. Do a left rotation, okay, from 4 to 6, or that means it is now hanging on 4, not 4. Okay, I need to rotate, do a left rotation so that it hangs on node 6. Do it, please. Let us try it. I know this red black tree is boring. I'm interested. Even I did not find any application really for this black tree. From next week we will see something new. That will be interesting. This week, until this week is boring.
I'll be honest, actually do find it interesting. I've been implementing the red black tree with the
Implementation is something. I said that I did not find any implication. That's what the implication of red black tree.
So the 5 would break off into the 4, right?
Please do it. If you don't have.
I didn't. I couldn't stop by the house to get my stuff. After work.
You can bring at least a pencil and some paper.
I left my backpack. I was late for work. I left my backpack at home.
You can go more. No, not solving. I said the term is not solving, the term is rotating. Left rotation. We need to hang this DST on 6. That means we need to make 6 as a root. Yeah.
All right.
No, including 4. Including 4. Yeah, you're correct. Okay, now, no. Okay, now it is explained. Okay, so you put all red. Okay, take another pencil. Now tell us, let us explain that whether it is a red black tree or not. Is there another color?
I don't see
marker?
him.
No?
Mm-mm.
Okay, so the on the node you can write R for red and then B for black. 6B for black, yeah. And then red. Only for the red typing R. That should be fine.
Okay.
Okay, by default it's black, okay? 9, 8, 9 and 11. Okay. Now explain me. Explain us whether it is a red black tree or not.
So root node is black.
Okay. That is good. Which are the properties have it?
And 2. So this is 1, 2, 4. So right now we have the issue of 4 black in this branch,
Yes.
or path, and this is 3 black. So no in that case.
Yes. This number of black nodes in this class are not same, right? This is not a red black tree. This is a BST, right? What kind of tree? This is BST. It's a binary search tree, right? And it is pretty balanced. But it is not a okay, you see that, remember that data came all in ascending order, but if instead of AVL tree or a red black tree, if we would just draw a binary search tree, then it would be how it would be. How it would look like. Understand? If we draw it, if we drew it as such a simple BST. Do you remember the data elements? It came 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How do we draw the BST or BST? Simple BST with this data set. You remember BST?
Yeah. Can't remember right now.
Who can tell us who can draw the BST of the data set 1 to 11?
I can give it a shot, but I don't think I'm right. But you were saying it was an ascendant, right?
Yeah, data is coming 1, 2, 3, 4, 5 to 11.
We'll just do it over here.
First one. Yeah, I'm telling you data set 1.
Yeah. Wait, 1?
Yeah.
Okay.
The next one 2.
Then it'd be 3.
The next one 3.
Yeah. So just go
The
down.
next one 4. Oh, you are making a pyramid.
Oh, yeah.
I didn't ask for a pyramid. I asked for a BST, binary search tree. What are the properties of a binary search tree? Did you forget everything? Oh my goodness.
I'm just jet lagged, that's all it is. My brain's not working today anyways, at this point. I told you I would think I'm wrong, but.
Who can tell us? Ladies, you remember? What are the properties for a BST?
For PS2.
Okay, we started with AVL tree with the limitation of BST, right? We found that there are some limitations of BST, and it is our goal to resolve that limitation.
Yeah.
And we came for this difficult thing, like AVL tree and red black tree.
Well, my brain's not working back.
Okay, thank you. Who can tell us?
Was one where the children can only be 2 or less? Is that one of the properties?
Hmm?
Was one of the properties where children can only be 2 or less? No, I can't remember.
Does it involve in order?
You remember BST?
Does it still have to be to where the left children are less than the parent and the right children are greater than the parent? But it's not like left oriented where when you insert, that's a different binary tree where when something's inserted it needs to be a full or complete one.
Now, for instance, I'm giving you data set 1, 2, 3, 4, 5, 6, 7, 8, 11. And with this data set, in this order,
What would it look like?
how the BST will look like? cannot announce, but in BST, you just put the water. The water will come get data, you put accordingly.
Would it just be a line? It'd be a.
Yeah, try it, please. You're pretty close. You can erase this stuff. Yes, dot. All the way to 11, right? Yeah, so this is the property that in BST, right child is always greater than its parent. And left child always less than its parent. And there are only two children, maximum two children. There are children of maximum two. And in this case, there is a hidden child, like that is for leaf. That is not here, leaf. For all of these, there are leaves. So here there is leaves, like this. Leaves, leaf. Both are leaves. But we are not considering leaves. Okay? So where are the leaves for this one?
One side all the way down.
This is a leaf, 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 this is a leaf. And if it is last value, for instance, first I want to 6, then it's another leaf. Right? But we are not considering leaves. It's okay then. We know that there is a leaf. Okay. So this is the in case 11 it will go all the way in. So it's linear is going, right? In order to check an 11 whether an 11 exists or does not exist, we need to go all by one by one. So then the time complexity will be big O n, right? And here the time complexity will be log n, right? Every time is splitting half. So log n, that means we know that log of 1024 equal to log, we say base 2, right? 10 to the power 2, right? Sorry, 2 to the power 10. 2 to the power 10. That means equal to 10. So it will have only 10 levels. And in this case high, so the time complexity will be 10. That means we need only 10 search in order to find a by BST with 1024 nodes. Only 10 search. But here in this case, if it grows like this way, it will need 1000 in number of n, 1024 search. So which one is better? If you search 10 times or 1024 times, which one faster? 10 times, right? This is our goal to develop an algorithm that is logarithmic time complexity. So now become faster. So in that case, if we cannot do exactly, but we saw our goal to do ABL tree and red black tree so that it does not grow linearly and it becomes pretty or closely height balanced. That is our goal. Okay, so please don't forget this, because if you forget this, then how can we proceed? That was the foundation. So BST was the foundation for ABL tree and the red black tree, right? The concept of ABL tree and red black tree came from the limitation of BST, right? Okay. So in your test, I will give you something like this, and I will ask you to rotate. Okay, please practice this. Okay. Now in our next lecture we discuss deletion, how to delete a node. Deleting means a node, that means at any time you want to delete any node. You can delete 6, or you can delete 7, you can delete 10, you can delete 2. Okay, deleting is the leaf node is easy, but deleting inner nodes is difficult. If you want to delete the root, That is more difficult. So hopefully we will spend an entire lecture discussing deletion next lecture, okay? And then I will give you homework assignment on insertion and deletion algorithms, so that you practice and then you study and you do well. Okay, so now let us go back from this previous slide I skipped, because we went through an anecdotal example, just illustration, so that how it works. Actually, through this example, we applied almost all possible steps or cases in insertion algorithm for a red black tree. So in the book, if you see the algorithm, so insertion algorithm, so left rotate and right left. So you see that algorithm is very large, but in the pictorial view is easy, right? So try focus on this first. Okay. So insertion, we know that we started with a node with red, and then if it is a root only node, then we make it black. If it is not, then we checked all of the properties. And then if there is a mismatch, or if any of the properties fail, then we did some rotation or recoloring, right? So in the book, you see, if you open the book has the entire algorithm. This is the insertion algorithm. RB means red black tree insertion algorithm. You can give any name, but the book it gives this name. Okay, so let me. Okay, so here insert algorithm, it takes it. This is method. So algorithm, this is defined as a method. You know that, right? So and it takes two parameters. One is T for tree, and G is the new element, new node that you want to insert in a tree. Okay, it can be at any position, in any shape of a red black tree. So I'm just telling you what the steps is, what this mean. So it put T dot nil. Okay, that means y equal to T dot nil, and then x equal to T dot root. That initially it put x equal to x is the root. Okay, that what I wanna say. It says G dot key. Key is the G. Key is the new element. Okay, one thing that I want to say that here you need to understand what is G dot P. G dot means in object oriented programming we understand dot means off, right? So here this says G parent of G. So G dot P means you can remember this is a parent of G. In some books or in some cases you may see like this, parent of G. Something. If you see something, you must find the parent. This is not a method. This is parent of G. Okay, but here it says G dot P. Okay, and dot it says T dot root, that means root of T. Okay, and then it says y dot left, that means the left side of y. Okay, and G is the element we are, and the y dot right, that means right side of y. Okay, so we will come back the algorithm later, but you understand the main things, right? So here one thing that we initially we put G dot color of G in G new node equal to red. This is the starting point, as we said that, right? In an insertion algorithm, we start with a node with color red, right? Then after that, after inserting a red color node, then we check all of the cases, all of the properties, 5 properties, right? Whether it matches or not. So this is a greater part or a complex part in the insertion algorithm. Fix up. It is called fix up. Red black tree insert fix up. Fix up means whenever you are going to insert an element, in most of the cases it will violate one or more properties, and you need to fix those violation, right? So sometimes we will see that whenever we fix one issue, it will create another issue. So then we need to go all by one, we need to fix all of this. Ultimately it will be fixed. Okay, so the insertion fix up, let me go to the fix up algorithm. The fix up algorithm is here. Fix up is another method. So fix up is this T for tree and G is the new node to be inserted in T, right? So while it says, so as I said that here G dot P, that means read as parent of G. Okay. G dot P, that means parent of G. So then how do we read this one? How should we read this one? If we read this one as parent of G, okay, then how do we read this one? While
Color of parent of Z.
yes, color of parent of G is red, right? Okay, that means if or for loop, okay, if that while, that means while, that means it is a loop, right? So you have to start from the end and you go all the way up until it is not a root, right? Okay, so while color of parent of G equal to red, then you see there are three cases. You need to go proceed one. So if you see parent of G equal to, so if that means if parent of Z is the left side of, this means parent of Z is the left of parent of Z. In some books, or you may see that it is grandparent. Okay, parent of parent is grandparent, right? So some book it says means that GP, grandparent in some algorithms. So that means what is here is if G of P, the parent is the, because our key element is over here is G. If parent is the left child, okay, of left child of grandparent, that means if parent is the left side, then we have to do, so y, we need to put y equal to the value on the right side. And then now you see that there are very clumsy repeated steps. Then we need to do something so we'll come back then in algorithm. It says that sometimes we need to take care of the uncles. A child also affect uncle's color, not only parent color. We saw that a root, if needed, a root changes its color. Starting from red, it becomes black, and if that does not fulfill, then it can change its parent color. If that does not fulfill, it also changes its parent siblings, that means uncle's color. Okay, so this algorithm here, so you see that these are case 1. So it seems to me like these 4 steps for case 1, it seems to me clumsy. So in the slide, PowerPoint slide has a little bit simplified format. We will go to the slide. So there are 3 conditions, 1, 2 and 3, right? If, else if and else. That means 3. So that means order is not a matter. Even if you put this one first and if you put this one later and this one next, it will work. Okay, so that we saw that there are three cases: case 1, case 2, and case 3. So the you see book has this example, so I will ask you to read the through example. It is difficult for me. It's like this is I tried in another lecture to concise it, to make it small, and then try to read this, but I could not read it. It's very small. So in the book, if you have a book, it is 1 page, okay, and take one side and then read this figure description. Okay, what happens, for instance, in node A, after insert G, G is here, this one. Initially, like this. I'm lucky that I got it from my previous lecture. So initially, okay, initially this tree was like this, only the red part within red bundles. After inserting 4, okay, after inserting 4, it became the whole thing, okay. So then you see that when we insert 4, right, and then you see that 4 is the 4 parent is red, right? So it's as we know that if a parent is red, then its child must be black. So it violates that property, right? So in that case, a simple changing of this color from red, from this red to black would not work. Will not work. Simply let us see that. For instance, you may initially think that okay, so this child initially born with red color, and its parent is red, so let us make it black. Okay, but that would not solve the issue, because you see that, and in that case, if you make it black color, then how many black colors on the left side? 1, 2, and then 1, 2, and 3, right? So there is a mismatch. So that will not work. So instead, the algorithm says that fix-up algorithm said in that case, instead of changing its color, what do you need to do? Change its parent color. So not only so in this here, you not only change its parent color. So not only its parent color changing will not work. Okay. Then what do we need to do? We need to change its uncle color. So here, this one is 8. Is this 8? Is 8. 8 is the uncle of G, right? So if this is 5 is parent, then this is uncle, right? And then 7 is grandparent. Okay, and according to the case 1, so it says that it changes uncle color and grandparent color. So then it comes this way, and then change from G, from this, and G will be at this point 7. And so the while loop, it says the while loop, right? And then until we need to go all the way up. So then G initially was over here, and then G is over here. Finally, it will be like this. So there is a rotation after rotation. So these 2 steps are intermediate steps. After these intermediate steps, so this will be our finally and fixed version for this will be our finally and fixed version of this red black tree. This will be finally fixed version. And if we see that this one, it satisfies BST color, red black tree. So this is number of black node is 3, 2, and this size 2, and this size 2, and this side 2. So this is red, and then black, red, and black. So black is not an issue. So and these 2 are intermediate steps. Okay, so and then here, so in the intermediate steps, this one here case 2 is applied, case 2 here and case 1 here and case 3. These are the cases for these steps. These are the steps for here. Okay, and then I think if you take this in a book, if you read this through the book, then you will see, then you see and you understand. Read this, please. Read this description, then you will understand. Okay, now let me go through slide, because this I found a slide that has pretty simplified form, because instead of writing all of the cases, it says case 1, that case 1. If this, so the same algorithm, okay, insertion algorithm, instead of writing all of this, so this is different kind of algorithm. So the case 1, case 2, and case 3. Okay, so now let us see the case 1. You understand case 1. Case 1. Case 1, that if you say that in case 1, if J is uncle, G, what is G? G is the new element to be inserted, right? Okay, initially it was red. Okay, and then if J's uncle is red, for instance, over here, this is beta is G over, B is G over here. Okay, and who is this uncle? This Y, right? D value is uncle, right? So in that case, so this alpha, beta, gamma, delta, epsilon, these are leaf root. So if you can skip this, okay? Alpha, beta, gamma, and then you can skip this. But the book, I think the algorithm and the slides, they gave the alpha, beta, gamma, so that it's easy to check. In the final version, you know that alpha, beta, gamma, delta, epsilon, it come in order. Okay, or you could give A, B, C, D in lowercase a, B, C, D. Then it's easy for you to hear. For instance, you can check that alpha, beta, gamma, delta, epsilon, A, B, C, D, E, F, G, just to easily check that it is in order, correct order. So this is why they give leaf nodes, but you can skip the leaf node. But I think it's giving leaf node is easy to check. So here is G. Okay, so here G is if G is, now we are not looking is parent. We are looking G's uncle color. Okay, so if G's uncle color is red, okay, if G's uncle color is red, and if G is a left child or G is a right child, G is a right child of his father. You see that G is a right child of his father. Okay, and G could be left child of his father, or it could be right child, right? There are two ways. If, so number case 1, if G's uncle is red, okay, and if G is the right child of his parent, okay, then so then G's grandparent, so then G's grandparent must be black. G and parent of G are both red. So here this will match actually. This will be the situation. And what do we need to do? We need to apply these steps. These are the fixing steps. So what do we need to do? We need to recolor parent of G. Okay, recolor means it is red, then make it black. So we made it black. Okay, and also recolor is uncle. Okay, so uncle is red, then it makes black. And also recolor is grandparent. Now recolor his grandparent. Okay. Now if this one is so then next step is that make G upward. So this was initially this was the new root, but consider that since we need to check all the way up, so make the grandparent as the new G. Consider that this is the newly inserted element, and that in the next phase what it will go, this part will go together, this part will go together. This is the G, this is the new node, and this is branch. Take the branch for the other stuffs. Okay, so the concept over here, for instance, or if you think that this is the last one, this is last piece, we do not have any more branch, then we need to do one more thing, right? What is the last step we need to do? If this is the root, then we need to make the root black, right? Then it will be done. You see that in that case, if this is the only, there is no more, and if this is the root one, in that case, then we do not need to go up, then we need to just recolor it. So then it will be black, this will be black, and this will be black. So there are two blacks on both sides, and it's okay. It matches all the properties. Okay, so what is the first condition? If G's uncle is red, and if G is the right child of his parent, we face the situation, right? What did we do? We change its parent color, we change its uncle color. Okay, we make the parent color black. Okay, and we also change the grandparent color, and we step up. This is the case 1. Okay, does anyone has any question about case 1? So if you understand case 1, case 2 is easy understand. Okay, now let us go to the case 2. For case 2, almost same, but if you say if G's uncle is red, but G is the left child of its parent. So here this is G, you see A, this is G. Previously that was here, right? That was here. So in that case, since it is a BST, so that was A was here and B was here. So you see that the example, if you take side by side, if A was here and B was here, but in this case, why B is here and A is here? Because this is a BST, right? You have to maintain the rule, BST. So here then what do you need to do? Change this parent color to black, okay, and uncle colors to black, okay, and grandfather color to black, to red, to. Okay, this step is given over here. They could change it here. So and then make the uncle color is red, okay, and move up G from here to grandparent. So this is now this will be the final unit, and this unit will go within your next steps. And if it is the only one part, then we need to do one more thing, right? What is the last one part? If it is the only one, so this is root. If this is root, then we need to recolor it to black, and in that case there will be 2 blacks here, 2 blacks here, and then there is no issue. Why again, one thing that if they put alpha, beta, gamma, del, so then if say alpha, beta, gamma, they are this messes. That means if there are any more leaves or any more sub branches, it will go together. This alpha, beta, gamma means. Okay, so and this is the case 1. Case 1. I'm sorry. Case 1 has 2 steps. That's I made a mistake. Case 1 has 2. If this is left child or right child, okay, then case 2. Case 2 is comparatively easy. If G's uncle, sorry, the case 1 has 2 steps, okay, 2 steps. If it is left child or right child. If it is right child, then this one, and this is left child, then this one. And then step 2 is comparatively easy. Okay, in step 1 we saw that if J's uncle is red, right, and in this case we will see if J's uncle is black and if G is a right child. So then what we will do, so here, so now then what do we need to do? Now G is a left child and both G and red, and then red and case 3, make it case 3, right? So left rotation, okay. Okay, so in that case what it does, these two, taking these two, it does a left rotation with these two, this A with G and its parent, this is G including its parents, it does a left rotation. So if it takes a left rotation, then it will come B over here and A over here. So in that case this will fall in case 3, that in the next steps. Okay, now let us go to the step 3. And in step 3, okay, step 3 is if this uncle is black. So here is G is this one, right? So case 2 we convert it in case 3, and then now if G's uncle is black, okay, so then if it is black, then make it change its parent color first to black. This parent color is changed as black, and make it grandparent color as red, okay, and do a right rotation. So if you do right rotation, this is easy. So B will be root, and then C will go right side and A is left side. Then it is straightforward and there is no steps needed. Even it is root, then it is still black. So step 1, case 1 is more complicated. You have to check whether your G is the left child of his parent or right child is parent. And G in the first case 1, it checks if its uncle is red in both cases. And case 2, it will fall if uncle is black. Okay, his uncle is black, that is case 2. Okay, and G is the right child. And case 3, it will fall his uncle is black and G is the left child. So for case 1, it checks if uncle is red, and there are 2 situations: if it is his parents' right child or left child, then it goes case 1. Okay, these are more steps in case 1. And then case 2, if uncle is black and it is right child. Okay, and right child in this case, just we need to change it 3 steps. It's completely easy. And then case 3, okay, this is case 2. Case 2, okay, it's completely easy, 2 steps. Okay, and then case 3. So in combination of the slides and the book, please do some study and then understand it. I will give you some homework. So the assignment, next assignment is coming with insertion algorithm. Okay, and then if you use paper, computer, okay, then you have to draw colorful. Okay, and if you use paper and pencil to take the picture, then use a different pencil, red and black. Okay, and do some practice, please. It is initially clumsy and difficult, and I hope that from the next week you will get interest whenever we study other algorithms. Breadth first, searching algorithm, that will be interesting. Okay, and please do not forget to start the assignments and then quiz 3. Okay, thank you so much.